Hello everyone, I am Sayani and I'd like to welcome you all to my YouTube channel on Diploma and Engineering videos. Welcome you all to the first video of my subject hydraulics. Please watch this video till the end without skipping in between. In this video, we are going to learn the basic concepts of properties of fluids. My dear students, let us first understand what is matter. Matter is actually everything we see around us every day. Atoms and compounds are all made up of very small particles of matter. Those atoms go on building the things we see and touch every day. So how will you define matter? Matter is defined as anything that has mass and takes up the space because it has a volume. Volume is the amount of space that something occupies. Matter is classified into solids, liquids, and gaseous. Now, liquids and gases are collectively termed as fluids. Now let's understand what is a fluid. As I have told you earlier that any substance which is in the liquid or in the gaseous state is called as a fluid. Now we will differentiate between a solid and a fluid element. To make this concept clear, let us consider a solid object and a tangential force F is applied on it. As a result of this force, a deformation occurs in such a way that A moves to A dash and B moves to B dash. The deformation is consistent after the force is applied. That means the object will not deform further beyond this limit. The distance between A and A dash is marked as delta x. Vertical distance is marked as delta y. Therefore, shear strain will be equal to delta x by delta y. In case of solids, shear stress is directly proportional to shear strain. That means tau is proportional to shear strain. Let us now consider any fluid element and a tangential force F is applied on this fluid element. As soon as the deformation takes place due to this force F, A moves to A dash and the point B on this fluid element moves to point B dash. So deformation takes place gradually and A dash moves to A double dash and similarly B dash moves to B double dash. In case of fluid elements, further deformation also takes place and A double dash will move to A triple dash and similarly B double dash will move to B triple dash and so on. Therefore, we can say that in case of fluids, stress is proportional to strain rate. Now let's quickly check out some common examples of fluid which we see around us every day in our day-to-day life. First one is very important, that is water, without which no living beings or no human beings also can exist on the surface of the earth. Next is petroleum, alcohol, milk, gasoline, and yes, blood is also a fluid. Paints, glue, kerosene, benzene, ethyl alcohol, mineral oil, mercury, honey, which is also essential for intake of human beings for their well-being, oxygen, hydrogen, and any other liquids or gases which are not mentioned here in this video. Now let's understand what is fluid mechanics. Fluid mechanics is that branch of science which deals with the behavior of the fluids, that is either liquids or gases, at rest or as well as in motion. Fluid mechanics is classified into fluid statics, fluid kinematics, and fluid dynamics. What is fluid statics? The study of fluids at rest is known as fluid statics. Now, if we study the fluids which are in motion but the pressure forces are not at all considered, this is called as fluid kinematics. And if the pressure forces are also considered for the fluids which are in motion, that branch of science is called as fluid dynamics. So basically, fluid mechanics is classified into three types, that is fluid statics, fluid kinematics, and fluid dynamics. Now let's see where our subject, that is fluid mechanics and hydraulics, is actually applied in reality. In our civil engineering field, for designing a water piping systems for a city or township, we have to apply the concept of fluid mechanics. For designing a sewage system or a sewer, we have to apply the concepts and principles of fluid mechanics and hydraulics. The principles of fluid mechanics and hydraulics is applied for designing of water distribution system from a reservoir to either irrigation fields or in a township. It is also applied for determination of pressure head of a water supply system. Application of fluid mechanics plays a vital role in design of artificial hearts and dialysis systems in medical field. Many concepts of fluid mechanics are applied in design of aircraft, spacecraft as well as in design of cars also. What is hydraulics? Hydraulics has been derived from a Greek word hydro. Hydro means water. The subject hydraulics is that branch of civil engineering science which deals with water at rest or in motion. And the subject fluid mechanics deals with the branch of engineering science which deals with the behavior of fluids, that is liquids as well as gases, under the conditions of rest as well as in motion. Hydraulics is also classified into hydrostatics and hydrodynamics. Some of the applications of our subject hydraulics with respect to irrigation. First, application of hydraulics is necessary for calculating the discharge through a canal. For distribution of equal water supply in a township or in a city, or for irrigation or agricultural purposes, the concept of hydraulics is very important. To determine the velocity of flow in an open channel, we have to apply the concepts of hydraulics. In construction and design of dams also, the total pressure and center of pressure acting at the dam face has to be calculated using the principles of hydraulics. Application of hydraulics is also done in designing spillways. Now, let's learn some important terminologies which are used in hydraulics and fluid mechanics. And our first terminology is density or mass density. It is defined as the mass per unit volume of a liquid at standard temperature and pressure and is denoted by the Greek alphabet rho, and its units are kg per meter cube. Mathematically, rho equals to m by v, where m is nothing but the mass of the liquid and v is the volume of the liquid. Our next terminology is the weight density or the specific weight of the liquid. It is defined as the weight per unit volume of a liquid at standard temperature and pressure, and it is denoted by small w. Its units are kilonewton per meter cube or newton per meter cube or newton per millimeter cube. Now mathematically, W equals to weight of the fluid, that is capital W divided by capital V, that is the volume of the fluid. Now W or the weight of the fluid equals to mass of the fluid multiplied by acceleration due to gravity, that is m into g. Now volume of the fluid is V, and now my dear students, mass of the fluid divided by volume of the fluid, we have already studied, it is equals to rho, that is mass density, from equation number 1. So our equation will now look like W equals to rho into G. For water, weight density or specific weight is equals to 9.81 kilonewton per meter cube. If you convert it in Newton per meter cube, simply convert kilonewton into Newton. That means if you convert kilonewton into Newton, you have to multiply it by 10 to the power 3 or 1000. So W equals to 9.81 into 10 to the power 3 Newton per meter cube. To convert specific weight from kilonewton per meter cube to Newton per millimeter cube, simply multiply it by 10 to the power minus 6, because you are converting meter cube into millimeter cube. Why minus 6? Because meter cube is in the denominator portion. You can see Newton per millimeter cube. That means meter cube is in the denominator portion. So whatever is in the denominator, when it goes to the numerator, it becomes minus as per the law of indices. Next is viscosity. It is the property of the fluid which offers resistance to the movement of one layer of fluid over another adjacent layer of the fluid. It is also defined as the property of the fluid by the virtue of which it offers resistance to flow. Let us understand this concept with the help of a velocity profile or velocity variation near a solid boundary of the fluid diagram. This curve which you can see is called as the velocity profile. Now when two layers of the fluid, that is first layer is designated as 1 and second layer is designated as layer number 2. When the two layers of a fluid at a distance of dy, the distance between layers 1 and layer 2 is designated by dy. When the two layers of the fluid at a distance of dy apart move one over the other at different velocities, that is u and u plus du, the viscosity together with the relative velocity causes a shear stress acting between the two fluid layers, that is 1 and 2. The top layer, that is this layer, causes a shear stress on the adjacent lower layer, while the lower layer, that means this layer, causes a shear stress on the adjacent top layer. This shear stress is proportional to the rate of change of velocity with respect to y. It is denoted by the symbol tau. Mathematically, we can tell that tau is directly proportional to du by dy. In order to remove the proportionality sign, we have to introduce a constant of proportionality. So, tau equals to mu du by dy, and mu is the constant of proportionality, which is also known as coefficient of dynamic viscosity. Du by dy is the rate of shear strain, or it is called as the velocity gradient. Thus, we can say that shear stress is directly proportional to velocity gradient or rate of shear strain. From the above relation, we can find out the value of mu or coefficient of dynamic viscosity, which is equals to tau divided by du by dy. That means it is the ratio of shear stress to rate of shear strain or velocity gradient. Units of viscosity in MK system is kgf second per meter square. In CGS system, units is dyne second per centimeter square, or it is called as poise. And in SI units, unit is Newton second per meter square. Let us study in detail the CGS units of viscosity. We already know that dyne equals to 1 gram multiplied by 1 centimeter divided by second square. 1 poise equals to dyne second per centimeter square. So here the value of dyne is 1 gram into 1 centimeter upon second square. So we have substitute dyne as 1 gram into 1 centimeter by second square in this equation, and second by centimeter square separately. So here you can see second will get cancelled, centimeter square will get cancelled, and remaining is 1 gram by second into centimeter. So I have rewritten the equation as 1 poise equals to 1 gram by second into centimeter. Now you all know that 1 gram equals to 1 by 1000 kg. Now 1 gram is written as 1 by 1000 kg because 1 kg equals to 1000 gram. Similarly, 1 centimeter equals to 1 by 100 meter because 1 meter equals to 100 centimeter. Simplify this. So here 0 will get cancelled. So remaining will be 1 upon 10 kg per second meter. Now 1 upon 10 kg per second meter equals to 1 poise. So 1 kg per second meter equals to 10 poise. Now 1 centipoise is equals to 1 by 100 poise, and 1 by 100 means 10 to the power minus 2. So 1 centipoise equals to 10 to the power minus 2 poise. The viscosity of water at 20 degrees centigrade is 0.01 poise or 1 centipoise. Newton's law of viscosity. It states that the shear stress on a fluid element layer is directly proportional to the rate of shear strain. We have already studied that shear stress is directly proportional to the velocity gradient or du by dy, and in order to remove this proportionality sign, we have introduced a constant of proportionality, which is also known as the coefficient of dynamic viscosity. So shear stress or tau equals to mu multiplied by the velocity gradient. Now we also know that shear stress equals to force upon area. Put the value of tau as F upon A and simply do cross multiplication. So F by A equals to mu du by dy. Just transfer A on the right hand side of the equation. So it will be mu multiplied by A multiplied by the du by dy or velocity gradient. Fluids which obey the above relationship, that is tau equals to mu du by dy, such type of fluids are called as the Newtonian fluids. Example of Newtonian fluids are water, petrol, kerosene, glycerin, benzene and mercury. Some fluids are also there which does not follow this relationship. Such type of fluids are called as the non-Newtonian fluids. Fluids which obey the Newton's law of viscosity, that is the above relationship, are called as the Newtonian fluid, and which does not obey the Newton's law of viscosity are called as the non-Newtonian fluids. Common examples of non-Newtonian fluids are blood. The human blood itself is a non-Newtonian fluid because it does not obey the Newton's law of viscosity. Paints, slurries, pastes, polymer solutions, suspension of cornstarch in water are some of the non-Newtonian fluids. There are some pseudoplastic fluids also, such as gelatin, milk and blood, and some dilatant fluids also, such as starch suspension and sugar solution. Types of fluids. There are various types of fluids such as ideal fluid, Newtonian fluid, non-Newtonian fluid and ideal plastic fluid. Now let's understand what is an ideal fluid. Ideal fluid is actually an imaginary fluid, as all fluids which exist in nature has some viscosity with it. A fluid which is incompressible in nature and is having no viscosity is called as an ideal fluid. Real fluids. All fluids in actual practice are known as real fluids because a fluid which possesses viscosity is called as real fluid, and in reality all fluids actually possess viscosity. Newtonian fluid. A real fluid in which shear stress is directly proportional to the rate of shear strain is called Newtonian fluids. Examples of Newtonian fluid are water, petrol, glycerin, benzene, mercury and kerosene. Non-Newtonian fluids. A real fluid in which shear stress is not proportional to the rate of shear strain or the velocity gradient are known as non-Newtonian fluids. Type of non-Newtonian fluids are paints, slurries, human blood, polymer solutions, suspension of cornstarch in water, etc. Last is ideal plastic fluid. A fluid in which shear stress is more than the yield value and shear stress is proportional to the velocity gradient or rate of shear strain is called as the ideal plastic fluid. That's all for today. Thank you all for watching this video. Please don't forget to like this video, share it with your friends and don't forget to subscribe to my YouTube channel Sayani Chatterjee Ray, and don't forget to press the bell notification for instant updates.